Section 1.5, take it to the limit, introduces the concept of what a limit is and how do we find out what the value is that it takes. So the limit usually is a number. But let me explain the concept first so that you can kind of get a good idea of it. Limits are numbers. So a value just like anything else. Limits are usually the same value as the function. Okay? And limits also, they do not have to exist. So we've got these different things. So limits are numbers, right? They're usually the same value as the function, but that's not always necessarily true. And they don't have to exist. So let's think about that in reverse. So they don't have to exist. So think about limits in order to exist need a function to appear predictable. Now that is a very interesting statement. So what does appearing to be predictable actually mean? So think about as you're traveling from left to right. Okay? So I'm going to take this, I'm going to draw this. As I'm going left to right, you see that, all my moves make sense from the one before it. So like I'm kind of nice smooth patterns. If you look before a point and you look after a point, it kind of makes sense, right? I'm above before and I go below, and it's nice and predictable. Now, all sorts of things can happen. We don't have to be nice and smooth. Why does it keep doing that? It could be rigid. It can have sharp points. It's relatively predictable though, right? Because, this point here, it's got points before it that are above, points below it. If I look here, it makes sense. There are points connected around it. It's not like those places come out of nowhere. These places appear. So, one thing that you want to get yourself over is that the function value doesn't have to exist. So, sorry about the announcement. So, what can happen is that, let's say, what if we have a point, right? So our graph looks very predictable. Then we come up to this open circle, right? A value that doesn't exist. So long as the other side of the function comes to the same place, even though that value isn't there, even though there's a hole in the graph, because both of these, they agree, then the limit exists there, right? Then the limit does exist, and it's whatever that whole place is. So that's what we want to try to get to. Now we'll work through some problems, but you want to think limits need a function to appear predictable. If it's not predictable, in a sense, like, let's say we have a completely broken part. This side and this side, they don't agree. Then that limit wouldn't exist. So these are things to consider as we go forward. Now, how do we read these? So a limit works like this. We're going to say the limit as x approaches c of f of x is L. So it's going to be some number. It's going to have some value, or it's not going to exist. But that's the way we read it. The limit as x approaches c of f of x equals L. So keep that in mind when we're going through some of these problems. Now, how do you deal with a limit? Okay, so I'm going to do some very, very basic examples first, just to show you how this works. So what to do. The very first thing that you're going to want to do is try to substitute. So, substitute. Okay, so let's substitute one. So let's say I've got the limit as x approaches 2 of x squared. Well, this is going to be 2 squared. Voila, that's the limit. The limit is 4, right? The function x squared would be it'd be predictable that the function would take on the value 4 there. That's fine. If you plug it in and you get a number, good job. That's all you have to do. Now that's pretty simple. Now a lot of the problems that we do, we're looking at odd places where some things are gonna happen that are not great. So substitute is the first idea. So what happens if that fails? So let me show you some instances where substitution fails. So let's say we've got the limit as x approaches 0 of 1 over x. Well, if I plug this in, I get 1 over 0, right? Can't do that. Can't do that. So if we're dividing by 0, if substitution gives us, if sub gives a number divided by 0, the limit does not exist. Okay? That's just not going to happen. There's not a value. We don't know that number. So this is not a value that we can take. If it's a number over 0, very specifically, right? Any number divided by 0, right? Other than if 0 is on top. Now, we could also have a situation where, let's say, we have something wrong with both. Okay? So let's say we have the limit as x approaches 2, okay, of x squared minus 4 over x minus 2. Well, what happens when we plug this in? What we're going to we plug in 2, we get 4 minus 4 on top, which is 0, and we plug in on the bottom and we get 2 minus 2, which is also 0. So this means more work. So what the 0 means really is that this value of 2 is a factor. That's a factor of both the numerator and denominator. By plugging into the numerator and denominator, we've gotten 0 both times. So there's something in common. So we have to figure out what that is. Now, let's say we are looking at that one in particular. So more work. There's 2 up. So more work can either be factor or rationalize in order to find that hidden factor. Now here, when we look at the limit as x approaches 2 of x squared minus 4 over x minus 2, when we look at that, I can say that, well, this is exactly the same thing as what I can factor the top, can I? I can do x plus 2 times x minus 2. And I can get x minus 2 there. Well, since we have something in common, this is the same thing as the limit as x approaches 2 of just good old x plus 2, which now I can plug it in and get my 4. So what happened there is that I got 0 over 0. They had a common factor. I wanted to find out what that was. So I decided to factor. I found out that the common factor was x minus 2. And then once I eliminated that, I could plug it in. It's not about the value of the function, because this function here doesn't even exist at the point 2. But what it does do is it's predictable around it. This function behaves like x plus 2 all the time, except there's a hole in it, and that's fine. So we'll get some more our feet wet more with that later, but just realize that by plugging in at first, that's all you have to do. And then you just have to kind of react to what kind of situation you get. So one thing that I will say, so piecewise functions kind of the same way. So you're going to see piecewise functions written something very similar to this. So like f of x equals, let's say it's going to be like x, or hold on, let me write this again. Let's say it's going to be 1 over x when x doesn't equal 0, and then it's going to be 0 when x equals 0. So think about what this function looks like. You can graph part of it, but realize that we have to use the domain as well. So basically everywhere with this function, or where x isn't 0, it's going to behave like that. So it's going to look something like this. Okay. Now, when x is 0, the value is 0. So that point is there. Now, when we ask about limits and stuff, remember, it's about being predictable. Does the main part of the function, which is this, the blue part, and it says the does not equal part, does that part of the function seem to agree around what they're talking about? The purple part doesn't matter. The purple part is the value of the function at a place. That's not what a limit is. The limit is the predicted value of what it is, not what the actual value is. So we'll get into that a little later as well. But this is something very important that we want to go over. The very last piece is about solving systems of equations. Again, it's trying to find what x and y values work for a certain thing, but I think you guys should be ready for that.